Hi, my name is Oded Naor from the Technion, and today I'll present the paper Expected Linear Round Synchronization, the missing link for linear Byzantine state machine replication, or SMR. This paper was written with my advisor, Idit Keidar, and in this paper we implement a synchronizer which allows to synchronize correct processes to the same round with linear message complexity. This actually allows to solve Byzantine SMR for the first time with linear message complexity as well. Let's start by going over the model. The model is eventual synchrony. In this model, there is first a period of asynchrony, then an event known as GST, global stabilization time, after which a synchrony time. The upper message delivery bound after GST is denoted as delta. The system has n processes, out of which a third can be Byzantine, denoted here by F. And for simplicity, we simply assume that n equals 3f plus 1. Now let's look at some of the known results on the message complexity of deterministic consensus protocols. There is a known lower bound from 1982 by Dolev and Weinchuk, which showed that at least a quadratic number of messages are required to solve Byzantine agreement in the worst case. If we look at some of the known deterministic consensus protocols, we see that DLS from 1988 requires a cubic number of messages to reach a decision. BBFT and Ziziva require a quadratic number of messages. And starting from the blockchain area, protocols like Tendermint and Casper, Hotstuff and LibraBFT require a linear number of messages. Algorand uses a technique of committees to lower the message complexity. Now you might wonder what's the connection between this linear message complexity to reach a decision and the known lower bound. And the answer is that this message complexity is only once 2f plus 1 correct processes follow a correct leader. In fact, all the protocols here are deterministic, therefore they cannot circumvent the deterministic lower bound. We use randomization to lower the expected message complexity of round synchronization, which I will later define in this presentation, to linear. Now, consensus protocols such as Hotstuff can use a round synchronization algorithm to lower the overall message complexity of SMR to expected linear as well. Round synchronization is actually the bottleneck of protocols such as Hotstuff, and by identifying this bottleneck and lowering X message complexity to expected linear, we solve SMR with this expected message complexity as well. It's worth mentioning that our result is the expected message complexity because again, we cannot circumvent the known quadratic lower bound. So let's go over SMR protocols in the eventually synchronous model. Now, most SMR protocols are divided into rounds of use. They mean the same in our context here. A process is always in some round, and progress is guaranteed once you have 2f plus 1 correct processes which are in the same round. So let's look at an example. The axis here represents the round numbers, 4 through 8 in this example. And let's say that the SMR protocol is used to create a blockchain. So this is the current state of the blockchain. And we have 2f plus 1 processes currently in round 4. So like I said, the processes run the consensus protocol, reach a decision. So they add a new block. They move to the next round, again, run the consensus protocol, add a new block, move to the next round, and there we might have a problem. In this illustration, we have 2f plus 1 processes, but actually f of them might be Byzantine. So let's look at an alternative run. It's identical to the run we've seen before, but here we separate the f plus 1 correct processes from the f Byzantine ones. Again, in this example, the f plus 1 correct processes and the f Byzantine ones run the consensus protocol, reach a decision, move to the next round. They run the consensus protocol in round 5, reach a decision, and move to round 6. And then the f Byzantine processes decide to stop participating and drink a margarita. So we're left with the following situation. We have f plus 1 correct processes in round 6. We have f correct processes which are in some round behind. And the f Byzantine nodes which stopped cooperating cause the system to get stuck. The intuition behind round synchronization is how do we get those F correct processes, which are somewhere behind, to the same round as the F+1 other correct processes. So how do we use round synchronization to solve SMR? This is a quote from Hot Stuff paper, Theorem 4, and it says the following. After GST, there exists a bounded time period, TF, such that if all correct replicas remain in view V during TF, and the leader for view V is correct, then a decision is reached. So there is, in this theorem, there is this big precondition that requires all the correct processes to be in the same view for at least TF time, and also that the leader for that view V to be correct. And if this precondition holds, then a decision is reached. Now, this precondition is exactly what round synchronization is. Round synchronization guarantees that we have a period of time where all the replicas or all the processes are in the same round, and in that round, the leader is correct. So if we look at the Hot Stuff protocol, we know that it can make decisions with linear number of messages per decision. The missing ingredient is this round synchronization, which helps reach this precondition. So if we have Hot Stuff and a round synchronization modules, we together have a complete SMR solution. Now the round synchronization is randomized in our approach, and by using randomization, we're able to solve this round synchronization problem with a linear number of messages. We use randomization to circumvent the deterministic known lower bound, which is quadratic. It's important to note that we use randomization only for performance. The SMR algorithm itself is still deterministic. In the worst case, we'll have a higher than linear message complexity, but the algorithm itself will always reach a decision. So let's look at this round synchronization. A round synchronization module, which is parameterized by some parameter delta, has a single output round leader with two outputs, R and P. Now, when this round leader is output, it signals to the process it should enter round R and use process P as its leader. Now, the guarantee that this module gives is that for any time t during the run, there is always a synchronization time ts after t, and this synchronization time will last at least delta. So in an infinite run, we'll have an infinite number of synchronization times. Each of these synchronization events would last at least delta time. And this is exactly the precondition needed for Hot Stuff's Leibniz theorem. So this allows Hot Stuff to solve and reach an infinite number of decisions in an infinite run. Now, for simplicity, we divided this round synchronization module into three submodules. The first one is a synchronizer. It has a single output new round with an output R, and it signals to the process it should enter round R. And the leader submodule attaches to this new round R a process P, which will act as the leader for that round. The third submodule is a timer submodule, which paces the time after which the synchronizer tries to enter a new round, so that it doesn't try to enter a new round too quickly. The timer depends on this parameter delta to make sure that each synchronization event will last at least delta time. Now, the main complexity comes from the synchronizer submodule. This is a distributed task. It needs coordination with the different processes in the system. The other two, timer and leader, are local functions. They're computed locally. So how do we achieve a synchronizer with an expected linear message complexity? The way we do it is by what we call a relay-based synchronizer. It starts by randomly allocating F+1 different processes, which act as relays for each round. So let's look at an example. We have processes 1 and 2 currently in round 4, and they want to enter round 5, and process 3 is somewhere behind. And like I said, we allocate randomly processes which act as relays. So in this example here, we see that, I'm sure you've seen Game of Thrones, so you know that the first and second relays of round 5 are Byzantine, and the third one is correct. Now, the relays are used to deliver messages with a threshold signature. This is similar to what's done in Hot Stuff. So In hot stuff, the leader collects messages from the processes in the system. Once it receives enough messages, it turns them into a threshold signature and sends them to all the processes. So instead of having an all-to-all communication resulting in a quadratic number of messages, this allows to reduce the number of messages to linear by having all send a message to the leader and the leaders send a message to all the processes. So in this example here, let's say that we want to enter round 5. It starts by sending a message to the first relay of that round. After GST, if the relay is correct, we can expect a response within a timely manner because we know that there is an upper bound for message delivery. If the relay doesn't respond to us within a timely manner, we move to the next relay. Again, we start measuring time to see when the relay should respond to us. And if we time out, we continue to the third relay. Now, once a correct relay is reached and the relay receives enough messages, it can take those messages, turn them into a threshold signature, and send them to all the processes in the system. Now, for each round, the expected number of Byzantine relays until the first correct relay is geometrically distributed. This is the number of relays that we expect to contact per round. So it is geometrically distributed with a mean of 1.5 because there are up to a third of the processes in the system are Byzantine. So we have an expected constant number of relays we need to contact per round. Each relay receives a linear number of messages and also sends a linear number of messages. Therefore, the expected message complexity for this method is expected linear. Now, when you design a message dissemination method like this one, a relay-based one, then you should, when you design the protocol, take into account Byzantine relays. So if the first relay is Byzantine, it might act arbitrarily. It might, for example, send the threshold signature to only a subset of the correct processes. And therefore, when you design the protocol, you need to take that into account. Now let's look at an example for Byzantine relays and the problems that they may cause. So in this example here, we have F+1 correct processes in round 4 and F correct processes somewhere behind. And we see here only the first relay of round 5, which is Byzantine. Now, our protocol, which I'll show you in a second, requires that at least F+1 correct processes will always enter a new round. So we need that at least F+1 correct processes will enter round 5. If the first relay is Byzantine, it can, for example, cooperate with the F+1 correct processes which are currently in round 4, participate in the protocol, and only when it comes to the last message which causes the processes to finally enter round 5, send it to a subset of the correct processes. And then we might be in a situation like this. Only one of the correct processes receives the message from the relay. F correct processes do not, and therefore we get a split. Only one entered round 5, and we have 2 F correct processes which are stuck behind. We've seen that we needed some mechanism for process that already entered a new round, in this example here, the process that entered round 5, to help, quote unquote, the processes which are lagging behind. This is just one of the examples that you need to deal with when you have this message dissemination method. Now let's look at the message flow of the round synchronization algorithm. The first phase requires F+1 processes, which send a message to the relay. Relay 5.1 here indicates that this is the first relay of round 5. The first message is named the pre-commit message. The other 2 arguments, 5 and 1, are the relay that this message is intended to. And once the relay receives enough messages, it can send a threshold signature of that message. Here it's indicated with a bold and underlined font. When 2 F+1 processes receive the pre-commit message, they respond with the second message of the algorithm, which is a commit message. Again, when a relay aggregates enough messages, in the second phase, it's 2 F+1, it sends the threshold signature of that message. Now, as I've mentioned in this example, processes try to enter round 5. Therefore, until they receive the threshold signature of the commit message, they're in some round lower than round 5. Once the process receives the threshold signature of the commit message, it enters round 5. We've seen in the previous slide that we need to take into account when designing the algorithm using a relay-based system, the Byzantine relays, which might send the commit message, the commit threshold signature, to only a subset of the correct processes. That's why these two phases aren't enough, and we actually had to add a third phase, which we call the finalize stage. So even after a process receives the threshold signature of the commit message and enters round 5, it participates in a third phase, and that is to help processes which might be stuck behind to also enter round 5. That's why this protocol has 3 phases. After 2 phases, the process enters the round, but it still participates in the third phase. Regarding performance, as I've mentioned, the expected number of Byzantine relays until the first correct relay is expected constant. Therefore, the latency is also expected to be constant. In terms of message complexity, each relay receives an expected number of linear messages. Again, the expected number of relays is expected constant. Therefore, the overall performance is also expected linear. I'll try to explain briefly the correctness behind the algorithm. So after GST, if we look at the highest round R that the correct process is in, so again, let's look at an example, and let's say that there are F+1 correct processes currently in round 4 and F correct processes somewhere behind. The highest round that the correct process is currently in is round 4. And now they try those F+1 correct processes in round 4, try to enter round 5. And the guarantee is that if the first relay of the round that the processes are trying to enter, again in this example round 5, is correct, then round synchronization to that round will occur within 4 delta time. Again, delta is the upper bound on message delivery after GST. So again, let's look at the first relay. We only see here the first relay for each round. So rounds 5 and 6 have a Byzantine relay, and round 7 has a correct first relay, and round 8 again has a Byzantine relay. If the first relay is correct, as I've mentioned, round synchronization will occur within 4 delta. If the first relay is Byzantine, then we guarantee that at least F+1 correct processes will eventually enter that round with expected constant time. So in this example here, the F+1 processes in round 4 try to enter round 5. The first relay is Byzantine. Therefore, we only guarantee that at least F+1 correct processes will enter that round. Now, we use the first relay also as the leader for the SMR protocol. So we don't, if the leader is Byzantine, we can't guarantee that decisions will be reached. Therefore, we don't need to synchronize all the processes to that round. Therefore, we don't synchronize all the processes to rounds where the first relay is Byzantine. We only synchronize to rounds where the first relay is correct. So like I said, round 5, at least F+1 processes enter. The same goes for round 6. But in round 7, since the first relay is correct, we guarantee that within 4 delta, all the correct processes will synchronize to that round. And that will happen within 4 delta time. Again, for round 8, the first relay is Byzantine. Therefore, we only guarantee that at least F+1 correct processes will eventually enter that round. So in an infinite run, we have an infinite number of rounds with a correct first relay. Again, relays are randomly chosen. Therefore, the probability that the first relay is correct is about 2/3. And in an infinite run, we'll have an infinite number of rounds with a first correct relay. Therefore, an infinite number of rounds where the processes synchronize and allow the SMR protocol to reach decisions. So let's summarize. In this paper, we formally define what round synchronization is, and we define it as a separate problem. We also give an algorithm that achieves this round synchronization with expected linear message complexity and constant latency under Byzantine failures. This algorithm is exactly the missing ingredient which allows hot stuff to solve SMR with linear message complexity. And to the best of our knowledge, this is the first SMR solution with expected linear message complexity. So I want to thank you for your time and for seeing this video. And that's it. Thank you.